I'm excited to be here. This is a fun stage to be back on. We'll talk a little bit about that in a minute. But before we do, just so you know, not like you have a choice, but what we're going to talk about next is large language models and prompt engineering for developers. So it's this little secret thing you probably haven't heard a lot about, this thing called AI. You've never heard of it. I'm going to be the first to introduce you to it, and we're going to go through it today. Hopefully, some of you have actually played with it. What we're really going to do today is strip away some of the magic of large language models and generative AI. This is 30 minutes, so I can't teach you how to do anything in 30 minutes, but I hope to at least give you some direction. So as you start to think more about how do you make AI part of your process, how do you build it into your apps, you've got some jumping off points to get into. By way of my own introduction, as Alyssa said, I'm Todd Anglin. I'm currently at Microsoft with our developer advocacy team, which focuses on a number of different things, everything from generative AI and AI tools to all the new co-pilots, things like GitHub Copilot, which I'll talk about tomorrow. If I don't meet you here at the conference, and if you want to connect after, you can find me on all the social medias at Todd Anglin. I would love to connect with you after today's event. Now, before we get into the main topic for today, and I'm going to keep the camera guy on his toes by moving back and forth a lot. This is not my first DevReach. This is actually me from DevReach 2013, where apparently I'm blowing my own mind, probably that my demo was working. So I'm just curious. I think this is the first year DevReach is back in Sofia. How many of you were at one of the previous DevReaches here? Okay, about half of the room. So welcome back to DevReach. Hopefully you've come to a few of these. Maybe I've seen you at one of these in the past. DevReach 2013 wasn't my first DevReach. My first DevReach, you have to go all the way back to 2007, which was the second iteration of DevReach, which was in a little room, like a classroom down the road here. I think we had one classroom, and this was a Telerik developer at the time, Risto Deshev. Some of you may know him. Apparently talking about how to sharpen the developer saw. So all said to say, DevReach for me is something I've been part of for a long time. I love this conference, happy to see it back here. And I hope those of you that are here for the first time really dig into it, meet each other, because you all are the experts here that can share a lot of knowledge with yourselves. So fun to be back, but here's what we're going to do today. We're going to talk about large language models, not for the data scientist, but for the developer. What do we need to know about this mystery topic? How do we peel the onion here and understand what's going on? Well, first, it's valuable to understand that this has been something that's been developing for a while. The field of artificial intelligence actually has its roots all the way back to the 1950s, 1960s, over 70 years ago, when we first started thinking about how do we take these big things that fill a room called a computer, how do we start making them think more like a human? And so in these early days, the work around AI, around artificial intelligence, really was just about how we get machines to mimic human thinking. And so there's a lot of very basic approaches here, and a lot of this time period was defined by the sci-fi interpretations of AI. We've seen the movies, we've seen the memes. The exciting bits of AI at this time were more fiction than fact, but we were starting to think even then, how do we make computers think more like humans? And as we marched through time, through the 90s and even into the more recent years, computers got more powerful, computing power got more affordable, and we could start to teach computers how to teach themselves. And so we had emerging sub-disciplines within AI, like machine learning, where machines can go look at large amounts of data, and from that analysis, without being taught what to do, without being programmed, they can discover the connections between things and become capable of predicting what should happen next. That evolved with more math and more things that are well beyond what I can actually do, into things like deep learning, where we have neural networks, which really mimic the way a human brain works in making connections, all the way to what we're talking about now, which is generative AI. And generative AI is really just an evolution of that, wherein we have now a trained model, a thing which taken a lot of input about what exists, and can create a new output that is similar to what it has been trained on. So that's the generative bit of it, whether it's text, whether it's an image. I've seen generative AI for music, for speech. The whole idea is you've got a lot of examples of what have been done before, and now we can create a brand new example from that. So we've been on this journey, and now we're talking about generative AI, a subset of artificial intelligence. And as we move into this is also shifting the way that we develop these models. Traditionally, and I say traditionally as in within the last 5 to 10 years, if we were going to develop an AI model to accomplish something, we would tend to do it very task-specific. So we would go find some data specific to our task. Let's say, as an example, a classification model, something that can identify things. The first thing we would have to do is go find a large data set of the kinds of things we were attempting to classify, and we would have to manually label that data. So these models would have to be trained on things that humans, us, the meat bags, would go in and attach labels to so the machine knew what it was, which means it's time-intensive, it's expensive, and we have to do it for each kind of thing that we want to have an AI model do. So this works fine, but it's slow, it's costly, and it requires us to spend this process over and over again, spin this process up over and over again for each new thing we may want to do. As we move into large language models, sometimes also called foundation models, the approach is different. Now we're saying, hey, wouldn't it be great, rather than creating a new model for each thing we want to do, what if we just fed everything into one universal model, and from that, we were able to complete all kinds of different tasks, maybe even novel tasks we haven't even thought of, because the model can see the connections between our data. And that's what's happening with the large language models you are seeing out there, the foundation models, is that they are being trained on these massive amounts of data. And from that, they can then complete a whole host of tasks without changing the model that you're using. So some of these models you may have heard of, obviously things from OpenAI, the GPT family of models, so GPT-3, 3.5, now GPT-4. Google has had a large foundational model for a while called BERT. Meta, you've probably heard of their open sourcing models around Llama, Llama 2. Even Microsoft has a model based on some of these meant to be more efficient called Orca, and there are hosts of others. I just put a few examples up here, but these are the foundation models, the big models that can be reused and repurposed to do different things. And as time has gone on, as these models have evolved, so too has their size. And what we often think about when we talk about the size of models is the number of parameters that these models operate on, the number of different things, the number of different tokens that they can identify patterns between. So if we go and look here at an example, the BERT large model from Google going back just a few years, it had 340 million parameters. And fast forward just a few years later, GPT-3, which is not even the latest version, it's now operating on 175 billion parameters. That's a significant change. And I don't do math well, but that's a much bigger number, I can tell that. Anyone know how many parameters, so to speak, that the human brain has? Any guesses? I mean, some of us are going to be different than others, so let's assume the smartest ones in the room here. Trillions of parameters, like 6 trillion, I think, is what the estimate is. Maybe a little bit more than that. GPT-4, which is not represented here, OpenAI has not published, they've not stated how many parameters are specific to GPT-4, but the estimates are somewhere in the neighborhood of 1.5 trillion. So another huge leap beyond what you even see on the screen here, like 10x. So these models are very rapidly getting more capable, which means they can also do a lot more things. They have novel uses that we haven't even yet thought of. So getting better, getting faster. We all know the story of computing, which means it'll also hopefully get cheaper over time. So how do these things work? How does the magic work inside of a large language model? For a lot of us, we've interacted with ChatGPT, we've used Bing Chat, we've used DALL-E. What's actually going on behind that black box? Let's run this as an example. We'll do this a few times today to kind of see how this works, but we'll just start with our model, our black box, and we're going to feed it things and get things out of it and talk about how that happens. So let's say I have my model, I feed it my prompt, and my prompt is, the capital of Bulgaria is. And I'm expecting my model to complete that, and it may complete that as Sophia. And it will complete that because it has a whole host of knowledge it's been trained on, and it understands the linkage between what my prompt is, what I'm asking the model to do, and what the most likely correct token is, most likely correct completion is to that prompt. My prompt gives the model the direction it needs to create a completion. Where does the model get this training data? What is it based on? Well, at this point, it's essentially the entirety of the open internet. All of the text, all of the academic articles, all of the white papers, all the things out there that have knowledge are used to train these models. And different models are clearly trained on different data sets. But what else does the internet have? It has blogs, it has user-generated content, it has comment sections, it has Reddit comments. All of that is also in most of these models. So if anyone has ever told a lie on the internet or has written a conspiracy theory which may not be correct, there's a chance, a good chance, that that data is also in the large language model. Because large language models, they are unsupervised as they are trained. They benefit from just having more data, not trained and tagged data. So this is a bit of kind of a warning and a call out to you as you work with these, is to understand all of this is in there, why it's important for you as a developer to make sure your applications, as they use this technology, understand this and build the correct guardrails around this, depending on your scenario. So the output of a large language model is dependent on the data used to train it and the prompt as input. So that's one of the key concepts I'll give you today as we work through this. Understand what that training data is, and I think as Scott mentioned this morning, understand that that is a point-in-time training. Most of the models you interact with today were point-in-time trained through 2021 or 2022, but they don't have up-to-the-minute data. We have to add that via things like our prompts or other techniques like retrieval augmented generation, or RAG, which you saw Scott do this morning. So let's try another example here. I have a prompt. Hi, my name is Todd. Who are you? The model completion is, hi, Todd. My name is Risto. Oh, it's a nice Bulgarian prompt. Nice to meet you. All right, that makes sense. It gave me a prompt. It gave a relatively understandable completion. So then maybe I say, you can give me a nickname if you like. Sure. How about Kel? Kel is a really weird choice to go from Todd to Kel. Why did this happen like this? And Scott mentioned it a bit this morning in his keynote demos, but it's because models don't inherently have any memory. They don't know what was said before unless you include that in your context of your conversation. So when you use something like Bing Chat or use something like ChatGPT, behind the scenes, you don't realize this perhaps, but it's doing all of this for you. It's structuring a conversation. It's returning or transmitting the entire history of your conversation with every interaction you have. Because if you don't send what's been previously said and responded, then the model has no idea that you've had that conversation before. So once we do this with our context, hi, my name is Todd, hey, cool, nice to meet you, give me a nickname if you like, now it knows, sure, how about T-Dog? Still not great, but at least now there's some context for how we got to what the nickname is. So here's your second key takeaway. Large language models have no memory and do not learn. They are fixed in time, and the only way they know anything else is either through your prompt or what you feed them when you're trying to get a response. So you have to do that work as a developer or use tools like we're shown this morning to achieve that. So let's keep going here. Let's ask it to solve a problem for us. Hey, model, what is the cube root of 9,261? For anyone in the room who's not a human calculator, the actual answer is 21. The completion says cube root of this number is approximately 21.6. It's not approximately anything. There's an actual answer to this. Let's try again. Hey, model, what are the top 5 movies listed at Rotten Tomatoes URL? Model says these 5 movies. Well, first of all, it's not 2019, so that's not correct. And also, I don't even know if that's correct for 2019. It's kind of hard to go back and find out, but that's certainly not the right answer to that URL right now. So this gets to the point that large language models cannot perform actions. They have no ability to go out and pull new data in from the internet. They can't perform calculator-like operations. It can just simulate answers based on its training data. The way you work around this is by using things like, again, we saw this morning, that allow us to build plugins or extensions that can add that context to perform specific operations, like Scott showed, getting the current date time and pulling that into our answers. But on their own, large language models cannot perform actions. You as a developer need to handle that and bring that into the flow. Make sense? I can tell, good. So behind all of this, the flow here, the thing that models are working with is something called tokens. And you may have seen it on the screen earlier this morning. And the general idea is that some number of tokens are fed into the model, and you get the next best token out, or you get a token out. Next best we'll talk about. And all of this flows, and the reason this matters is through something called the context window. And the context window is the total amount of tokens that a large language model can work with. And as you have a conversation, your context may grow bigger than that overall window, which means that parts of your old conversation may get lost or may get truncated as the conversation continues. And that's because within that context window is everything you or the user has said, their prompts, their inputs, and everything the model has sent back. All of that is inside of that context window, and for the models that you've heard of, things like GPT-3 or GPT-4 now, those limits are very real. So the most common models today have a token limit of about 4,100 tokens. GPT-4 has two flavors. There's one with an 8,200 token limit and a much larger one with a 33,000 token limit. But even in that one blog post I think we saw Scott try to load this morning, I think I saw on the screen it was like 155,000 tokens, something like that. So this token limit is something you're going to have to be intelligent with how you work with it, using things like embeddings and vector databases for storing those embeddings, which I think the next talk will get into even more, so you can learn a bit more about that. But know that this limit is something that you as a developer also need to really account for when you add this to your applications. You can't just put everything in and forget about it. You have to work smartly with that token limit. And what is a token? It depends on the model. You can kind of think of a token as a part of a word. Sometimes it's a whole word. It's not always a whole word. You can see here an example of a sentence. We need to stop anthropomorphizing. It's a big word. ChatGPT counts as 11 tokens, 43 characters. And you can see in some places it's not being split on a word boundary. Some words, like the large word in the middle here, are actually being split into 3 tokens. Tokens matter to you because tokens are often they matter because of the previous slide. They're a limit you have to work around, but they're also often what a large language model is priced on. How many tokens you're working with and exchanging is directly aligned with the pricing you'll pay. So understanding tokens in your applications and how you work with them is also critical. There is a website here. We won't go to it for time if you want to play with this. Platform.openai.com/tokenizer. You can actually see how the OpenAI tokenizer works, put in your own content, and see how it gets cut into tokens to give yourself an idea of this in your context. So here we are then. We're feeding some number of tokens in. We're getting the next token out. And this layer, so all the previous tokens go into the next response to give us the next token in our overall chain. But it's not giving us the same token every time, and this is part of what gives large language models that real kind of clever human feel to them. What it's actually returning is a probability of tokens that can come next, a probability table from which a large language model samples from that probability table the token that you actually see. And the kind of return we get, the kind of sampling we get, depends heavily on something called temperature, which we'll talk about in a minute. But the key from this is that large language models are not deterministic. What does that mean? It means they don't give you the same thing every time. They give you variety. They give you unexpected responses. Again, that's what kind of makes them fun when that's what you're after. But they are not deterministic. They will not give you the same thing every time, which can be a real pain when we're used to writing software that's supposed to do the same thing every time. So you have to think about that as well in your testing and how you're going to account for that. So let's try this out here. Name a country. Name a country. Maybe it tells me, or it returns a list behind the scenes of possible tokens to complete that have these weighted percentages of what that answer might be. And Canada will be the answer it gives me here because it has the highest percentage, and I have a temperature of 0.7 here to help influence that answer. Now, temperature can usually be anything from 0 to 1, and that will have an influence on the kind of answers we see. So as an example, if I change this to 1, we can see how my distributions shift here, where now it's a little bit less likely. It's going to be a little more creative in the kind of answer it may give me. I'm far less likely to get Canada and get one of the other answers when I ask this question, whereas if I make my temperature 0, For that prompt, for the prompt, name a country without any other context added, if my temperature is 0, it's going to give me the same completion every time. Now, that doesn't mean that it's deterministic. That means that for this specific prompt, I'm not going to get any kind of probability variation in the completion, but any change to that prompt, including history or previous answers, will affect then the next completion to the same question. So temperature is the main concept here. Play with temperature, understand it. Lower temperature reduces variability, means if you have temperature of 0, you're going to get less creative responses. Higher temperatures increase the likelihood of unexpected completions, which can be good. For the right scenario and the right application, those unexpected completions are part of what allow us to use this for things like creative writing or generating images. And so it's not always a problem, it's just something you need to account for in your use of it. So here's an example again, with my temperature set to 1 for very creative. Write a biography of Risto Rotikop, founder of the DevReach conference, include references. Anyone know Risto Rotikop? I hope not, because that's not a real person and not the founder of the DevReach conference. And yet, when prompted, the model gave me back. Risto Rotikop is the founder of the DevReach conference, a software development conference that takes place annually in Bulgaria. He has over 20 years of experience and a LinkedIn profile with a link. None of that's real. It's all made up. So you have to be aware that a model that is not grounded in your prompt or in other forms is more prone to hallucinate, to make things up. And that's what we have here. So your grounding of a model is key to getting back information, and an ungrounded model is a risk. It also means that there's no switch inside of these models, as convenient as it may be at times, to just switch off creative mode and go to fact retrieval mode. These are not fact retrieval systems. That is, again, where you have to use the retrieval augmented generation, the RAG model, or prompt engineering to get back the information you expect. So ungrounded models are a problem. We, as developers, need to ground our models to make sure that we are getting back responses that are useful to our users and they're not hallucinations like we saw with the DevReach conference. There are many ways to go about grounding models, but to give you kind of a brief intro to a way, let's look at prompt engineering, and that's how you interact with a large language model. So prompt engineering, what is it? It's a concept that says, you embed a description of what a thing should do, and then the model gives you the results. And you've probably done a little bit of this in your own testing with things like ChatGPT or Bing Chat. You've put in sentences, asked questions. All of that is a prompt. And the more information you give a prompt, the more likely you are to get back an answer that matches what you were trying to get out, the desired results. So as an example here, using the Azure OpenAI service, we can give a few different prompts and see that the prompt has a heavy influence on the kind of answer we get back. So very basic, write a tagline for a trip to a planet Nura. No other context, we may get back this. We may get a nice, simple response. Or a prompt like this, which has some schema for a table, and then we ask it to create a SQL query for that schema. We can get back code, and we can see this in things like GitHub Copilot and tools designed to help us with code, and we'll talk a lot more about that tomorrow. Or even more interesting, perhaps, we can say, give me an image, a photorealistic image of this planet, and get back image data. So each of these different prompts gives us wildly different kinds of responses. All of this is prompt engineering in its most basic form, and you as developers can have a lot of influence on how these things perform, what they can do for your applications, your users, through prompt engineering. And there are 3 concepts I want you to think about when it comes to prompt engineering, 3 concepts that come from this space, and that is zero-shot prompting, few-shot prompting, and fine-tuning. 3 approaches to prompt engineering that can influence your results. Zero-shot prompting is something like this. My prompt says, headline, coach confident, injury won't derail the Warriors topic, and then I get a completion from my large language model. The coach is confident the injury won't derail, blah, blah, blah. Zero-shot prompting basically says, without providing any examples, Ask your model for a completion and just hope it gets it right. I think of this a lot like the Google "I'm feeling lucky" button. You're just hoping that the model understands what you're after and pretty much gives you what you're looking for without any other coaching. And for certain kinds of things, this actually works fine. But what often helps is if you give the model a little bit of training. And this is what we call few-shot prompting. Few-shot means, hey, we're going to show you a few examples, or maybe even one example of what we're trying to get done here and the format that we're after. And then what a large language model will do is, on its own, from that, derive what the right response should be. So here now we have a few examples of headlines, and we show that what we're actually after is a single word topic to summarize that headline. So we've given it 3 headlines, 3 topics, and now again we give it the headline, "Coach confident, injury won't derail Warriors," topic, and now when the model responds, it knows, oh, I see, you're after a single word, and we get basketball. So few-shot prompting helps us guide the model towards the kind of response and format we want when we're working with prompt engineering. The last approach here, and arguably also the most complex, is fine-tuning. And fine-tuning says, hey, my task is pretty specific. I have my own set of tagged data that helps describe my task. So I can take an existing pre-trained model, let's say a GPT-type model, and I can make a copy of it and then add to that model my target data set, which has been tagged, it has been described, and what that will do is actually adjust the biases and the probabilities of the kinds of completions the model will produce when you start using it, as we have for all other models up to this point. So it allows you to really tailor the model and the way it does completions to your domain-specific knowledge, assuming that you have that. But it is more advanced. It can be more expensive because now you have your own model to copy and maintain, but it is an option out there for the right scenario. So the guidance here, start with 0-shot, then few-shot, and if neither of them works for what you're trying to do, then look into fine-tuning. And there are a lot of tools now on places like Azure to go help make that process easier, but it is still an option of last resort as you're getting into prompt engineering. And then finally here, to leave you with this as kind of a wrap-up, because again, we're just getting you introduced and I'm moving us along. As you go about integrating these large language models into your deterministic programming environments, you're going to need tools to help make that a little bit easier to manage. And here's some examples of some open source frameworks that will make that job just a little bit easier. All open source, all out there for you to check out. TypeChat, from the makers of TypeScript, as you might expect, helps you add schema to the responses you're getting from a large language model. So you, as a developer, expect things to come back in a certain format. Let's say you're a coffee shop and you expect people to order coffee in sizes. You can now define that schema so that when you get responses back from a large language model that are free and open, you can start to find and match, hey, is that part of my schema? Can I plug that into a thing that my rest of my code understands? TypeChat is there to help you do that. Semantic kernel, you saw this morning, a way of helping you orchestrate those flows between your plugins, retrieving additional data, retrieving additional context, and feeding it into the large language model. That is there for .NET, for JavaScript. And LangChain, very similar, another open source project for Python, for JavaScript, all about helping you figure out, how do I make this part of the flow of my code? How do I add the extra context programmatically to provide better answers to my users? Make sense? Yeah, kind of, maybe. So at the end of the day here, we've cracked open that these things are not magic. They are token predictors. How you prompt them and how you train them has a heavy influence on the tokens you get. And as developers, you need to manage much more of what's happening, the history, the context, the added prompt flow engineering to make this useful in your environment. So summarizing, large language models can generate text, code, images, human-like output, provide information, create novel content. We've seen that. We met Risto Rotokope here. Very novel, very creative. Large language models do not recall facts. There's a great article on The New Yorker, if you check out that link there, that summarizes that a large language model is not a fact database. It is just a JPEG of its training data. It's got this fuzzy picture of everything it's learned, and from that it tries to pull out its responses. It's not a fact engine. They do not learn, they can only be augmented, and they do not act. They cannot go search URLs, they cannot go do a calculation. That has to be done through plugins and integrations. All right, I've hit zeros. If you want to learn more about this topic, if you want to find more resources, if you want to find great blogs and videos, use this QR code or go to learn.microsoft.com/AI. Otherwise, great to have you all here at DevReach 2023, and I hope you enjoy the rest of the conference. Thanks a lot for my time here.